Today we're going to be talking about the difference quotient. So the formula is f at a plus h minus f at a all divided by h, where our h cannot be 0. So the difference quotient can be used to calculate the slope of the secant between our 2 points a and f at a, and a plus h and f at a plus h. Now, if you think back to the slope formula that you know, y2 minus y1 over x2 minus x1, and you plug the points in that we have here, this is really just the simplified version of what we would get. So just to finish it off here, this formula generates an increasingly accurate estimate of the slope of the tangent at the point A as the value of h approaches 0. So the closer h gets to 0, the closer the slope of the secant is to the slope of the tangent. As h approaches 0, the secant, so the formula that we had on the previous page, f of x plus h minus f of x all over h, approaches the tangent of f of x. So you can see this right here. We're going to be using this a lot, and it means approaches. I guess I used it up here as well. So in other words, the limit of the secant as h approaches 0 equals the tangent. So in the next few slides, we're going to be talking about what limits actually are. So if you see here, I have a function drawn in red. The most important thing to note here is that I do have this point, a, f at a. So remember, this f at a is the y coordinate, and it is the function at point A. There we go. So what I have on the right here is basically just words describing what's happening. So f at a is the y coordinate at x equals a, so that's what I was talking about here. This next little bit, the limit as x approaches a of the function f of x is equal to f of a. So basically I've just plugged this a in here instead of my x. And then again, just saying it different, the limit of f of x as x approaches a equals f at a. So for example, as x approaches the value a, f of x approaches the value f of a. So if I approach this point a, whether I come from the left or the right, I'm going to end up at this point f of a. On the next slide, I am going to go through some specific examples, so if you don't like this general form, the next slide is where you'll probably figure it out a little bit more. So we're going to get into an example here. So I have my first example, f of x is equal to 2x. I'm really sorry, it's kind of squished in there. I do have a graph of y equals 2x as well. So this first limit says the limit of f of x as x approaches 1. Now, the next line is kind of written in there for us. So what I've done here is I've replaced this f of x with my 2x because that's what my f of x is in this particular example. So the limit as x approaches 1 of 2x is right here. So on my graph at x equals 1, I can see that that limit is 2. Now, it is just as easy for this one because this is going to be the same if we approach from the left or the right. I can plug that 1 in there. 2 times 1 gives me 2. The next one says the limit as x approaches -1 of f of x. So again, I know that my f of x is 2x. So the limit as x approaches -1 of 2x, I'll put that blue dot in there as well. So this is an x of -1. And I can see on my graph that that is going to equal -2. Or again, I could just take this -1 and plug that in there. So my next example says the limit as x approaches 2 of 2x minus 3. So I should recognize this. This is just another linear function. It is continuous, so we're not going to overthink this. I'm going to go ahead and I'm just going to plug this 2 in here for x. So 2 times 2 subtract 3, that limit is just equal to 1. And if we were to look at a graph, if we were to plot y equals 2x minus 3, as x approaches 2, this graph would equal 1. In this example, we're going to be talking about one-sided limits. So find the limit as x approaches 2 of x squared minus 3. I have drawn in that parabola here for you. So I know that if I just plug in 2 squared minus 3 is 1. So this is that important point right here. Now if I take a look and I approach 2 from the left, that's the green arrow I have drawn in here, that limit is going to equal 1. And the exact same thing happens if I approach it from the right. Again, the limit as x approaches 2 from the right is going to be 1. So I've just written this out here. So as x approaches 2 from the left, x squared minus 3 approaches 1. And if I'm going to write this out again, the limit as x approaches 2, and I'm going to put a little minus sign here, that represents from the left, x squared minus 3 equals 1. And then again, as x approaches 2 from the right, x squared minus 3 approaches 1. So if I were to write it out, I would say the limit as x approaches 2, and I'm going to have a plus sign here to represent from the right, x squared minus 3 equals 1. So what we can say now is that the limit as x approaches 2 of x squared minus 3 exists only if the limit as x approaches 2 from the left, remember this superscript with a minus sign means the left, of x squared minus 3 is equal to the limit as x approaches 2 from the right of x squared minus 3. So in this case, because when it approaches from the left it was 1, and when it approaches from the right it was also 1, we can say that the limit as x approaches 2 exists. For the last little bit, we're going to be talking about continuous and discontinuous functions. So our first little point here, I guess, is that if our function is continuous at x equals a, then the limit exists. So when I look at this function, I could draw this function without lifting my pen up. I can see that at the point A, I have this blue dot right here. Basically, what this means is that the limit as x approaches a from the left of f of x is going to equal the limit as x approaches a from the right of f of x. So this is exactly like our last example. I forgot to add this in earlier, so I'm going to add it in now. So what I can say here is that the limit as x approaches a, I'm not going to say right or left now, I'm just going to say a in general, of f of x is equal to f of a. So in this next point, we have discontinuous at x equals a, and the limit does not exist. So when I look at this graph, I'm not able to draw this function without lifting my pen. I can see that this point at a is closed, and then up here I do have an open point where my graph continues. So what this is basically saying is that the limit as x approaches a from the left does not equal the limit as x approaches a from the right. So if I, just again, if I were to draw some arrows in here, coming from the left and coming from the right, I'm not getting the exact same point. So if I were to summarize this, I could say that the limit as x approaches a of f of x does not exist. All right, and our third and final point here is a discontinuous function at x equals a, but the limit exists. So when I look at this graph, I wouldn't be able to draw it without lifting my pen. If you think about last semester, there's a hole here. So when I take a look, if I'm approaching from the left or I approach from the right, I am approaching the exact same value. So I could say that the limit as x approaches a from the left of f of x is equal to the limit of f of x as x approaches a from the right. But because I don't actually have a value here for f of a, I can't give my limit an exact answer. So I'll use green just like the other ones. So I am able to say the limit as x approaches a of f of x exists, but it does not equal f of a like it did in that first point there. In the past, I found that these are the trickiest types of examples for students to understand, so I thought I'd just go through one quick example with you. So I have a graph here. It's kind of like a piecewise function. It is not continuous. So when I take a look at this first limit here, it's the limit as x approaches -1, and I see the superscript, so from the left. So I'm going to approach -1 from the left, and that limit is going to be, let me count, 1, 2, 3, 4. Now, if I approach, we're going to do the second one here. If the limit is x approaches -1 from the right of f of x, so that's coming this way, that is going to equal 2. Now, because this limit from the left and the limit from the right are not the same, the limit as x approaches -1 with no superscript here does not exist. So I hope that clears it up a little bit now that you see an actual example with some numbers.